Hey there, welcome back to the second part of practicing making a system diagram. This is David Sellers. I'm with Facility Dynamics, and I'm assuming that you got to here because you did the first part of the exercise where you took the either the virtual model, this chiller plant, or the screen capture as you watched the video where I gave you a little tour of the plant, and then you've tried to make a system diagram. And what I want to do in this clip is show you how I'd go about making the system diagram and what one of my answers would look like, and then use that diagram to explain how a variable flow primary secondary plant works, and also show that how one very small difference in how you pipe that plant could make a huge difference in how it worked. So to get started, I'll just advance here and show you one of my diagrams. This would be what I would consider a right answer, I guess you could say. But there's not one right answer. I'll show you a second, quote unquote right answer here in a minute. But first, let's just talk about how I got this in the first place. And to do that, I'm actually going to draw on the slides here. Let me get my pen going. And so, one of the hardest things about starting one of these things out in the field, especially if you're in a real mechanical room and it's noisy and it's dark and there's 10 or 15 other systems layered in on top of the one you're trying to look at, is to figure out, where should I start? You may have never seen this kind of machinery before. And the truth is, it doesn't really matter where you start as long as you just pick a spot that you can recognize, identify, and say, well, there's my, frame of reference. It started right there. So a lot of times I might, if I'm in a mechanical space like this, I might pick where the lines come through the wall, which is just after, the service valves right here. So, I may start this diagram on this piece of pipe right here. And so I'm just going to label that A. Okay. And there. And so on this picture right here, that would, this piece of pipe right here, somewhere on that pipe is point A. And then I'd literally, take my little laser pointer if it's up in the air, or my flashlight, or if it's down low, my hand, and just sort of follow the pipe. And you'll remember from some of the previous posts on system diagrams, in the context of a system diagram, the elbows are meaningless. So I really wouldn't document those 245s. I would just keep following the pipe until I came to a T. And here's a T right here. So we'll call that point B. And that point on our drawing is right here. And I should point out that seldom does your first system diagram come out looking this organized. In fact, if you go back and look at, where I'm showing how I drew the one on the Energy Center roof, it's a bunch of totally disorganized pencil sketches the first time that I then make several passes at reorganizing. The point here isn't so much to show you that as just to sort of show you how I'd go about tracing it out. So anyway, we get to this T, and now, I'm an older guy. I'm not a parallel processor. I'm a serial processor. So I can't follow the two pipes at the same time. I got to pick one or the other. And since I'm kind of interested in the equipment, I probably would, and there's no right or wrong answer here, I'd probably pick the branch of the T that goes to the pumps and just figure I'll come back to the run of the T. And incidentally, on a T, the part that goes straight through is called the run typically, and the part that leaves the side is called the branch. So I'm going to follow the branch of this T, and if you look at your screenshots or in your model, you can see that this actually goes up and turns and comes to another T. And that other T is this T right here. Keep doing that. So we'll call that point C. So there's point C on that drawing, and here's point C on this drawing. So now I got to make a decision again, and I can pretty easily just look over and see, well, there's another T hooked almost directly to this one and a capped valve. So I might go ahead and put some notes there. So that's point D. Point D. And up here, point D is right there. Let's make that a little better here. tell you what, I'm going to erase the D and make that a little cleaner. Okay. So there's point D. Not sure why it's so sensitive down there, but it seems to be. Okay, so there's point D. So now, I need to follow one of the, run branches out of the T's, and I might, since I'm at point D, I'll just follow that one, and it goes down through the pump. So we're at point D, we drop down through the pump, then we come out of the pump, and I document, the service valves, the check valves, anything that could affect flow. Like if I closed it, it could have shut the flow off. A check valve keeps flow from going backwards. A control valve modulates the flow. Anything that could affect flow I include on the drawing, any piece of equipment. And so I drop into this pump, I go through the pump, and I come out of it, and I follow that over, and I come to the chiller. And I come to the chiller specifically, the one that has no hot gas bypass and no VFD. So, here's this pipe, the service valves, the suction diffuser, the pump, the check valve, a couple more service valves. And this is the chiller, and, since they're different, I'm just going to note that. It might have, it might be important to know. So there's no VFD, variable frequency drive, on that chiller. You come out of that chiller, you go through the service valve, and you come to another T. So what are we at? We're at A, B, C, D, E. So this will be point E. Right here. And on this drawing, point E. And again, like all the other T's, I've got to make a decision. If I look right over, I can see that there's another T, we'll call it point F, with the flanged and capped valve, and since I'm right there, I'll probably note that. But then I'm going to go back through the chiller, because I'm sort of suspecting that's going to take me back to my pump at this point. So sure enough, I come through the chiller, go through the service, or I'm sorry, come through the service valve, go through the chiller, come back out of the evaporator, and go through another service valve, come up, drop down. I'm on the discharge side of the pump, so there's a service valve and a triple duty valve there and a pump, through the suction diffuser, and I come out through a service valve, and I end up back at point C. So now I actually have most of this circuit, or that complete circuit, traced out. Now, just a little subtle point. The pump actually has a triple duty valve on the discharge, which is one piece of equipment. In this drawing, I actually drew them as two to show its function. The triple duty valve is a check valve and a service valve and also a throttling valve. I could have used one symbol that I would then define as a triple duty valve. I just happened to use two symbols to show the functionality. And so I might, put a note on here and say, write TDV, just to remind myself that that's actually one piece of equipment. And I might even take a picture. I do that a lot when I'm making these system diagrams, because then you can go back and put all the details in. So I've got this traced out, but I haven't followed the other side of the run from point F. So if I follow that, pipe makes an offset, but it's just elbows, so I'm not too worried about that. I come to another T, we'll call that G. And lo and behold, if I look at that, just a couple feet across the way is point B. So here's T, G, and this long piece of pipe on the drawing is actually a very short piece of pipe in the field. And that's also a characteristic of a system diagram, because you're untangling it. So you can make the pipe as long as you need to make the diagram orderly. It's not about pipe length and elbows. It's about showing the system in an orderly, untangled fashion. If we go on from G, we come to the 2 points where the pumps drop off, and so we'll call them H and I. And those are these points here, H and I. And I imagine at this point you're getting the idea. So rather than keep going, I'll just say, so there's our system diagram, and that's how I do it. And again, it probably would have evolved from a series of pencil sketches, not excuse me, not anything that came out this neat and orderly in the first pass. But that's that's how it is. In other words, that's exactly the order. If you were a water molecule, you'd see the equipment in that order going through the diagram, through the system, and that's really important in terms of diagnostics, that you reflect what the water molecules are going to see. Now, I said this is one right answer. This is another right answer. If you were to go through the process we just went through and trace all it out, you'd discover that the order of connection here is exactly the same as it was in the previous. The only difference is that I basically untangled a little bit more. If I page up, maybe you can highlight that. What I essentially did was I sort of folded this into here and then flattened that line out. And basically it just took a couple bends out of it, made it even more straightforward. And as we talk about how the system works, you probably will see some of the features I'm going to talk about more readily just because of that little nuance, that little change. But either one of those drawings I would consider correct because it got the order connection right, it's orderly, it's neat. Now, I said, for the purposes of our exercise, we were going to assume that the loads on the system were across the mains and two-way valves. So let's go ahead and get our load drawn on here. And then we'll talk about how a variable flow primary-secondary system like this works. So there is an air handling unit. That'll be like typical of many, we'll say. And pipe comes out of it, put a two-way valve on it. And there's probably service valves and stuff that I'm not bothering to draw right now in the interest of just getting to the explanation of how this works. So, now to understand one of these, there's a couple important concepts. I'm going to make some sketches or some marks on here with a highlighter, and then we'll switch to another slide to talk in more detail about the actual nuances and details of how this works. So we pick a highlighter. If you look at this, there's actually two independent circuits here. If these pumps weren't running at all, and these pumps were running, and the valves were open on the air handling units, I could pump water around in a loop that kind of went like this. Okay, so that's basically a distribution loop, and these would be called the distribution pumps. The flow of these pumps, because there's two-way valves on the air handling units, is going to vary. And as these valves throttle as the load drops off, they'll basically restrict the flow. And if I didn't do anything else, if I just had pumps sitting there, no variable frequency drives, no variable speed drives, I would shove the pumps up their curve. In other words, I'd reduce their flow rate at the expense of producing more head. And that actually saves energy eventually. And I'll refer you to the pump class slides for the details of this, but I'll just make a real quick sketch because we kind of could use a pump curve for some of the things we're going to talk about anyway. Oops, now I got a funny color. Black. So if you remember anything about pump curves at all, it's basically a plot of flow on this axis versus head or pressure on this axis. And for a fixed speed with a fixed impeller size, the pump is going to operate on a performance curve that, the shape of that curve is purely a function of the pump's geometry and the way it's designed. On a typical pump curve, if you were to plot the brake horsepower lines, constant brake horsepower lines, they would sort of go diagonally across the curve like that. Meaning if the pump was out here on its curve and you started throttling it, at first you wouldn't make much change in the horsepower because the brake horsepower line is sort of parallel to the curve. But as you shoved it, this is called shoving it up its curve, as you pushed it further and further up its curve, you'd start to cross basic brake horsepower lines. So even though you're making more head, you're moving less water, and you win in terms of energy. So throttling will tend to save energy. And truth is, back in the olden days, when I first started messing with this stuff, variable flow systems were really unusual in the early 70s and before that, because it was very expensive to actually vary the speed of something. Like my first variable flow system was a variable volume air handling system, and I designed it in the late 80s, and at that point in time, for a 40 horsepower motor, I chose an eddy current clutch as my variable speed mechanism, because I could get one of those for about $20,000, whereas a variable frequency drive would have cost me about $50,000 and also would have been about as big as 2 motor control center sections, like about twice the size of the gray box here running that chiller. So there's been a big change in that technology since the mid-70s. And if you want to know more about that, we're doing a class at the Energy Center in early December on variable speed drives. But that said, we used to just let these valves shove the pumps up and down their curves, which would vary the flow in this distribution loop. Now, in newer systems, we usually have some sort of pressure sensing mechanism either at the pumps or out at the field if we're optimizing stuff. And as this valve throttles, the pressure tends to go up. The sensor sees that and says, oh, I can run the pump a little slower, and slows the pump down. So instead of being shoved up and down the pump's impeller curve, you end up moving the system around on the pump moving around on the system curve for the piping system, which is a parabola that kind of looks like that. So instead of going like this to get to the reduced flow, so you wanted to end up here, the valves would shove you up the curve to get there. The variable speed drive brings you down this system curve to get to that point. So you can see I've exaggerated it in the drawing, but you can see that saves significantly more energy. So that's why it's an attractive technology. So the whole reason we did that was it lets the distribution pump energy vary with flow. At high loads, you'll move a lot of water. At depending on if you're using a variable speed drive or just moving around the curve, you'll move a lot of water and use more energy. Then as the load drops off, you reduce the energy requirement. So that's a good thing. And this design evolved as the first energy crisis hit. The problem was, and you might say, well, gosh, why didn't you just vary the load through the whole shooting match, including the chillers? Well, at that point in time, the chiller control technology wasn't good enough to let us vary the flow much in the evaporators. You absolutely never allowed the flow to vary in the evaporator of a chiller. And the way we did that before the energy crisis was we just put three-way valves out here on these air handling units. The pumps basically pumped the chillers and the loads. They pumped about the same amount of water all the time. The pumps had to have the head they needed for the chillers and the distribution piping network and the loads. And so you had constant flow high head pumps running continuously. And so by going to this system design, we decoupled those two things. And so far we've talked about the variable flow loop. So now let's talk about the other loop that exists in this system. And I'm going to switch back to the highlighter, and I'm going to switch to a different color. So there. The other loop that we have in the system, if you were to turn those pumps off and then turn these pumps on, water would, generally speaking, go around in a circle like that. Now, technically a little bit of it would go this way, unless that valve was closed. But this piece of pipe, physically is very short, very large relative to the flow rate. So the water, most of it's going to go around in a circle like that. Now, that's sort of the magic. You'll notice that these two loops share a piece of pipe, and that piece of pipe is typically called the decoupling bypass. Oops. So this piece of pipe right here is called the decoupling bypass because it serves both of the loops, but it sort of magically allows variable flow to the loads, but allows constant flow to be maintained to the chillers, which seems magic, but it's actually just applied physics. And so let's talk about that a little bit. If we go back to this pump curve for a minute, Guess we'll pick red. The pump physically, if it's at a fixed speed and I'm not changing the size of the impeller, it physically has to work on this line. And so what that means is if I don't change the head that pump sees, then I will always maintain a fixed flow. So if as a designer I size the piping that's common to both of these pumps and to this loop, so it's generously sized so that no matter what the flow is, there's virtually no pressure drop in it. Okay, so that means this header right here that's shared by both pumps, this piece of bypass, and this header right here that's shared by both pumps. If I make that generously sized so that there's virtually no pressure drop, whether there's design flow going this way or a little bit of flow going this way or even reverse flow, that means the head this pump sees is pretty much set by the piping in this circuit. And short of somebody moving a valve or the evaporator plugging up with debris, that head will never change. So what that means is this pump, when it runs, always sees the same head, no matter what's going on out in this system, because of how I designed it. And so if it always sees the same head, it's always going to move the same amount of water, and that's how the magic happens. That lets the flow in this distribution loop vary while the flow through the chillers was maintained at a constant rate. And so to some extent it let us have our cake and eat it. We could pick these pumps for the high heads and flow rates the loads needed, and these pumps just had to be picked for the flow the chillers required at a very low head. There's really not much head required to push the water from here out to the chillers and back. I've had jobs where these pumps were picked at 15 or 20 feet. So newer plants, you can actually vary the flow through chillers. Current technology chillers with PID controllers versus proportional controllers, which is what the older chillers had, can tolerate more flow variation. And the risk when you vary the flow is, if you're making really cold chilled water, the refrigerant of course has to be colder than that. And so say you're making 38-degree chilled water, the refrigerant temperature is going to be approaching 32. And if it's 32, that's freezing. So if the refrigerant got to 32 because of a proportional band or something like that in a proportional control system, you'd start building frost up on those tubes, which would restrict the flow, which would make a bad situation worse, and you could freeze the chiller up, which is a very serious thing, believe me. So in the olden days, proportional controllers on the chiller, not so tall, there's an error band. You couldn't, flirt with varying the flow. Now we can. So newer plants, instead of this decoupling bypass, they'll have a bypass with a control valve in it that maintains the minimum flow required by the chillers. But once you're above that minimum flow, this valve closes and it is fully closed, and you vary the flow through the chillers along with the loads. You get rid of these secondary pumps or these distribution pumps, and the pumps that are pumping the chillers do everything, but they're also variable speed pumps. That's a different conversation from the one we're having, but I was just trying to sort of contrast where we are now versus where we came from and why this whole design evolved. The bottom line is this design evolved because a constant volume system had big pumps pumping a steady amount of water under all operating conditions at a lot of head. The energy crisis hit. We figured if we could somehow decouple the flow to the loads from the flow through the chillers so that we could vary the flow to the loads with the load requirement, we could save a bunch of pump energy, and this design lets us do that. So now let's actually look at how this design works under a couple load conditions. So and I just, the background just changed to look a little more closely at the piping, right here, so you can see it better. I'm going to go ahead and draw my air handler back in. With my two-way valve. Okay, so there's my circuit. And just for the sake of discussion, just pure discussion, I'm going to stick some numbers on these. I'm going to say that this is a 500-ton plant. So at 2 GPM per ton, that means at full load there's 1,000 GPM going out to those air handlers, that each of the chillers are equally sized, so 500 GPM here, 500 GPM there. And I'm going to page up just for a minute. So that's the no VFD chiller. I just want to make a note of that. So you'll remember from the first video, that's the chiller we would like to, when it ran, oops, VFD. When this chiller ran, we'd like it to just run at a steady load. And when this chiller ran, it's the one that has the features that let it follow the load more closely. So this is the one you'd like to see, be able to pick up the load swings, and this is the one you would like to run flat out when it ran. Okay. These pumps, there's a bunch of different ways you could make a decision about these pumps. It's not the point of our discussion, so I'm just going to arbitrarily say the designer designed the system so that at full load, at full load you ran both of these pumps, and so each pump at full load would be doing 500 GPM. And again, there's some redundancy considerations associated with that, but not the point of our conversation right now. So let's look at what's going on here at full load. At full load, we'd have 1,000 gallons per minute coming back to the plant. And you get to this T. Okay. Now, at full load, both of these chillers are running, so you got 500 GPM going here and 500 GPM going here. So here's where you have to believe in physics. At this T, unless we create or destroy water, if 1,000 gallons per minute is coming in this way and 1,000 gallons per minute is being taken out by those pumps going that way, at this one load condition, there's no flow in that piece of pipe. And it's purely by virtue of how we designed the system. And you have to believe again in conservation of mass and energy. But if 1,000 gallons per minute come in here and we don't create or destroy water, and 1,000 going out there because of how these pumps were selected and designed, there's no flow in this bypass. Okay, the water comes out of the chillers. 1,000 comes this way, and then 1,000 goes out to the load and completes the circuit. Okay, so that's a theoretical operating point. In the field, there's enough noise in systems that there's always a little bit of variation going on back and forth. This will be 1,010 and this will be 990, and then it'll flip, because little things going on that affect things. But virtually no flow in this bypass at full load. That's how the plant's intended to work. Now let's unload the plant 25%. So I'll change colors. So now, let's say we're at 750 GPM 750 GPM. Get out of that. 750 GPM required out here at the load. So 750 is coming back to the plant right here. Now, when we get to this T, we still have two pumps running. Okay, and because we picked it that way, the head on those pumps isn't varying no matter what's going on out here. They're still going to take 500 GPM each, so there's still going to be 1,000 going this way. So if a 750 is coming in and 1,000 is going out, and I'm not creating or destroying water in this pipe, the only way I can get that extra 250 is to have it reverse and flow backwards through this pipe. So at part load, you start to reverse flow in this plant design, and that takes cold water from the discharge of the chillers and mixes it with the warm water coming back from the plant, or from the loads. I'm sorry. And so that means this temperature goes down, and that's fine. This temperature goes down. In the first instant that happens, the chiller's running at full capacity, it sees its leaving water temperature start to drop, its control system backs its inlet vanes off, and it unloads the chiller to match and, match that entering water temperature and the capacity required to maintain it. And so the chillers unload. We're at part load, the chillers are unloaded, all is well with the world. But not exactly. Okay? If you'll remember, the whole reason we think at least, the whole reason this machine had a VFD on it was because we wanted this machine to see the load variation and this machine to always run at full load when it was online. But because the water blends before it goes to both of them, because this T is right here, that means that for this plant, the way it's piped, both machines are going to unload uniformly in terms of percentage. These are two equally sized machines, and so like at 75% load, they're 250-ton chillers, so they would have dropped back to about 225 tons each, a little under that. And so because they have the same entering water temperature, if they're controlling for the same leaving water temperature, that's just physically how they're going to work. If one machine was bigger than the other, the percent load on each machine would remain the same. So this sort of brings me to my point. If you're, say for instance, a control contractor, and the control sequence said, as the plant unloads, chiller 2 shall modulate its capacity to match the load, and chiller 1 shall run at full load, it physically can't work that way. It's a piping problem. Your control sequence can't make that happen, not without doing something like lowering this chilled water set point so that this machine has to work harder and is less efficient and makes colder water that then blends up, but then that creates some other problems. So you can't make this control sequence work because of a physical piping change. But if people don't recognize that, I'll guarantee you they'll be yelling at the control contractor, which in my little example was you, because your control system isn't operating the chillers properly. Fix your control sequence so that chiller 2 carries the load swings and chiller 1 runs full loaded. Unless you're a welder, you aren't going to be able to fix that. Okay? Now, to get that to happen, the plant had to be piped slightly differently. Okay, so as I step through the slides, I'm going to bring up another system diagram here that's going to show that in a schematic. But watch that section of pipe right there, because that's where the change is going to happen. Okay, this is how it's piped. That's how we wish it was piped. Now I'll back up. See, before tee up, you come back and drop to the pumps. Now, first pump comes right off the return as it goes into the plant. Second pump comes right off the return as it goes into the plant. There's that, capped valve for future, and the bypass goes this way. That system diagram, it looks like this. Okay, for the water to get to the bypass, it has to go past this pump first, and then this pump, and then to the bypass. Okay, that makes a real subtle difference, but it's important. It's sort of the key. So let's draw our air handler back in here. A little wavery hand there, wavery hand, but anyway, you get the idea. So there's our air handling unit. And let's go ahead and look at this plant at that 750 GPM, 3/4 load condition. So there's 750 GPM of flow. We come back to the plant and we get to that first T. Now remember, we're at more than one machine's load, so we got two chillers running. Each chiller is running at 500 GPM. So we get to this first T. There's 750 coming in. Since this chiller's taken 500 of it, it takes 500 GPM of warm water, puts it through the chiller. That chiller is running at full load. you get to this T, this piece of pipe. If we took 250 away, or I'm sorry, if we took 500 away, that means in this piece of pipe, there's 250 GPM going this way. When we get to this T, again, since we can't create or destroy water, the only way we can get the 500 that's going to go through that chiller is for 250 GPM to recirculate through the bypass. But now, instead of both chillers seeing that recirculated water, only this chiller sees recirculated water. Its entering water temperature tends to drop, which means it unloads, and this is the chiller with the variable frequency drive. So it unloads and, does its thing while this chiller remains at full load. Purely by virtue of this one piping connection is how that's made to happen. So for the control sequence to work, it also has to be piped like this, okay? And I'll put these slides up so you can look at them in the blog post and study that a little bit if you want. And also put up the plant model that shows it piped this way if you'd like to walk around in it. So that's sort of what I wanted to make, the point I wanted to make in this particular video clip. There's another interesting difference between a plant with the bypass here and a plant with the bypass here that I'll do a second video on in the next day or two, or probably more like a week till we'll get to do that. But for the time being, what I hope you learned from this is that A, how to go about making the system diagram, and B, that subtle differences in how something's piped can make a huge difference in how a plant's going to work. And I guess thirdly, I hope you have a better feel maybe for how a primary, secondary variable flow plant works. It's called primary secondary because it's got two different loops. One thing I discovered, at least in my experience moving around the country, like I lived in the Midwest from the 72 until 97, and then I went to the West Coast where I've been ever since. In the Midwest, we called the pumps that pumped the distribution system the primary pumps. I think the perspective being that the load's out there, so that's the primary purpose of the system. So they were the primary pumps, and the pumps that pumped the chillers were called the secondary pumps. On the West Coast, most people call the pumps that pump the chillers the primary pumps, and the pumps that pump the loads the secondary pumps. And so for a while I was having these really odd conversations with people because I'd be saying primary meaning this and they were thinking I meant that, and nobody's getting everybody. So I have started saying distribution pump and evaporator pump just so everybody's clear. And I know a couple other people have had that experience too, so it does vary where you are, and so you have to make sure everybody's on the same page when you say primary versus secondary pump. But that's why they call this system a primary secondary system. You've got the primary loop, depending on your definition, the secondary loop, and then the variable flow part is what's going on out there in that loop serving the loads. I guess before leaving, some people may be wondering, well, why would, if this is what the designer wanted. Let me get my cursor back so you can see that better, what I'm pointing at. Oops. So some of you might be thinking, well, if this is what the designer wants, how come it didn't get piped that way? Well, there could be a bunch of answers to that, but you got to remember, in the olden days, we used to draw a lot of piping isometrics like this. In other words, it was a two-dimensional way to draw a three-dimensional drawing. A lot of times people don't have the budget to do that anymore, so they have a piping plan, and maybe it's an 8th scale piping plan, and maybe there's, in addition to the chilled water system, the condenser system, the heating hot water system, the sprinklers, the steam system, the plumbing system, all those pipes laid out on it. And so it might not be clear just looking at the plan to the guy installing it how it's supposed to be piped. And maybe he was even a conscientious guy and he made a phone call to the engineer and said, gosh, I'm looking at your plan, I can't quite see how you wanted this connected up. Can you explain that to me or send me a sketch? And maybe the engineer is having a bad day and he said something like, you know what, you got the drawings, just put it in the way I piped it, or pipe it up the way I drew it. And so the fitter might have looked at a schematic, and the schematic on the drawings was wrong. It showed the other configuration because they forgot to edit it to show what they wanted in this plant. So he says, well, the schematic says that, and so I guess what they really wanted is the other piping arrangement, and he puts it in. I've seen that happen several times. I've seen it happen for lots of reasons. But the reality is it happens a lot. I and people I know are heroes on a regular basis just because we take the time to untangle the system, make a system diagram, and then figure out how it really is going to work based on physics versus how somebody hoped it worked based on a drawing that wasn't clear and a sequence that can't be executed given the physical constraints of the system. So I will stop here for now. Hopefully that gives you some feedback on your efforts to make a system diagram. And at some point down the road here, when I got to travel a lot this week, I'm going to visit my granddaughters, and so it'll be a little noisy where I am in terms of recording stuff, and when I have to really focus I go to a library, and so I can't talk there. So it's probably going to be a week before I make the second video that talks about the other nuance of this system that I wanted to bring up. So hope this was useful, and thanks for visiting the blog.